Hi, today I'm going to give a presentation on physics in for neural networks. I'm Abhranil Chandra, a third year undergraduate student from IIT Kharagpur. This is a seminar presentation. It is part of my coursework for Machine Learning for Earth System Sciences course under the guidance of Professor Albert Mitra. The outline for the presentation is we'll introduce the basics of neural networks, then we'll look into physics in for neural networks or PINs. We'll look into the application of PINs specifically to cases of Earth System Sciences, and then we'll conclude. Introduction to neural networks. We'll look into the basic idea and multi-layered perceptron. We'll look how gradients are computed through backpropagation, and we'll look how the loss function and optimization-based learning happens in neural networks. So the goal of a neural network is to learn a functional mapping between an input vector x and output y. Y hat is equals to f of x. The universal approximation theorem states that a neural network in theory can approximate any function however much complex it is. Now this function approximation is learned from input-output data through a parametric directed acyclic graph. Thus, y hat is equal to f of x comma theta, where theta are the model parameters consisting of the weights w and the bias term d. The parameters theta are learned by iterating over the data and changing the weights according to the gradients of the loss term through backpropagation. We'll look into both gradient calculation, backpropagation, and the loss function in the next slides. So on the right hand side, we can see the picture of a single layer of a multi-layer perceptron. A single layer perceptron can be written as y hat equals to a single function f of x is equals to phi of w transpose x plus b. This is the nonlinear manipulation on the affine transformation w transpose x plus b. Now to represent more complex functions, a single layer is insufficient. Thus, we create multiple layers, each having multiple neurons. This is a multi-layer perceptron or MLP. Each layer of neurons is associated with implementing a certain function, and multiple layers of such nonlinearities help us learn even more complicated input-output mappings. Thus, the final output follows a chain of multiple function compositions given by y hat equals to f3 of f2 of f1 of x. Here, I've shown the picture of a three-layer multi-layer perceptron. The first hidden layer is f1, the second one is f2, and the final output layer is f3. The image below shows how each progressive layer learns more complicated functional mappings and separation functions. Now we look into the backpropagation algorithm. Backpropagation is short for backward propagation of errors. It is an algorithm for supervised learning of artificial neural networks using gradient descent. Given an artificial neural network and an error function, this method calculates the gradients of the error function with respect to the neural network's weights. Gradients of a scalar function y is equal to f of x is given by simply the derivative of it, f dash of x equals to dy by dx. But gradients of a vector function, which is mostly used in neural networks, y is equal to f of x being the input vector belonging to R of m and y being the output vector belonging to R of n, is given by the Jacobian R belonging to R, Jacobian J belonging to R n cross m, such that the ijth component of the Jacobian matrix, is the differential of the ith component of x with the jth component of x. The use of these gradients is super important in both training neural networks and to incorporate physics-based constraints and invariances to create specific PIN architectures. Now we look into the loss function and the optimization algorithm. The loss function L of theta is a measure of how good the model predictions are, and thus is a measure of deviation or inaccuracy from the true values. We want to minimize the loss function or the cost, and this is the learning objective. The choice of loss functions depends on the nature of the problem. Mean square error or MSE loss is used for regression-based problems, and cross entropy loss is used for binary or multi-class classification problems. The learning algorithm used in neural networks is primarily some form of gradient descent, be it stochastic gradient descent or SGD, ADAM, or some variation of it. And it is used to adjust and fine-tune the weights of the neural networks by minimizing the loss function L of theta. Now the update rule is the new updated theta or theta new is equals to old theta parameters theta minus eta times gradient of loss function, eta being the learning rate, and gradient of L is calculated using backprop as discussed in the previous slides. Now we look in more detail what physics involved neural networks are. We, we look why inclusion of physical knowledge is important for neural networks. We look into a primer of differential equations. We look into methods to incorporate physical constraints into learning, and we look into some popular examples. The universal function approximation theorem only considers approximation errors, not trainability or generalizability of neural networks. Broadly, neural network performance is classified into three categories. First, the approximation error to the ground truth function, the generalizability to unseen data, and trainability of the neural network. Universal approximation theorem only considers the first one. Moreover, it provides no method to train a model to get that approximation. The naive method using the basis function in the previous slides can require exponentially large number of neurons even for approximating simple functions. Thus, it often becomes very tedious to train complicated functions. By incorporating domain-specific invariances, we can significantly improve the generalization properties of neural networks. For example, in computer vision, translational and spatial invariances are brought into by using CNNs. One reason CNN has been so successful in vision-based tasks is the translational invariance that is incorporated in them by design. We can see the performance on ImageNet classification using CNN systems since 2012 when AlexNet came, and recently with deeper and bigger networks, the error has reached superhuman levels. There are many more invariances other than translational invariances. For example, physics-based laws of nature like conservation of mass, momentum, or energy. But how to incorporate these invariances, and are these helpful? The image on the right shows a common view of how physics can help training. Even in big data regime, incorporating physics is often helpful. Moreover, if some boundary conditions are missing, or some physical laws are unknown for the system, or the data is noisy, or the physics laws are unknown, in such cases, pins can be very helpful. In low data regime, physics-based neural networks and physical invariances help to improve the generalization or regularized training. In the high data regime, using physical invariances can help make the model train easier with less number of parameters. Now the main question is, how can we incorporate these invariances into learning? First, we'll look into a primer about differential equations. Physics deals with the study of matter, energy, and their properties and interactions among each other. These relations are mostly modeled as differential equations, which are also used in pins as additional constraints. Example of a differential equation is shown below. This is a second order linear differential equation with boundary conditions. Now there are different ways to solve a differential equation. The most common being a closed form analytical solution, which often is used to solve simple differential equations as the one shown above. But for more complicated ones, analytical solutions are often not available, and thus finite difference methods are used. But recently, neural network-based pin approaches are being used, and the two key papers introducing this are the 2019 paper from Rice et al. And the Lagarde's paper from 1998. Now, the reason why neural networks are suitable for solving such problems are the key elements needed to solve a differential equation-based constraint problems are support for any functional form of the solution y hat is equal to f of x. Neural networks very easily ticks this box, as neural networks are universal function approximators and can approximate any function in theory. Neural networks also have the availability of derivatives needed to construct differential equations and arrive at a solution through backpropagation, chain rule, Jacobian, and Hessians of the derivatives, which are easily calculated and available through any auto differentiation softwares like PyTorch, TensorFlow. And neural networks can also act as optimizers. Now we look into the methods for incorporating physics into learning. The first method, and probably the most obvious one, is to train on massive amounts of data and hope that the neural network trains with good performance or generalization. Let's see the Burger's equation, which is a very famous partial differential equation used in modeling fluid dynamics, nonlinear acoustics, gas dynamics, or traffic flow. We see that taking lots of data from simulation of the Burger's equation, if we train a neural network and simply use a regression loss, we can train a model to fit the data. But the main problem is there are no guarantees that the model obeys the conservation laws, and moreover, it requires lots of training data obtained by simulating or from an actual physical system, and collecting such data is often not cheap or feasible. The second method is to enforce the physical laws as hard constraints, either in the neural network architectural design or in the optimization step. Incorporating physical constraints in the neural network architectural design is an open research problem. In CNNs, translational and spatial invariances are inbuilt in the architectural design of CNNs, but such architectural designs for pins have not yet been found. Optimization in neural network is a very difficult process in general. Over that, if you add differential equation based constraints as shown below in the image, the optimization process becomes highly non-convex, and solving such non-convex optimization using standard optimization schemes like ADAM or SGD, or even heuristic-based optimization schemes like LVFGS becomes very difficult. Thus, the most commonly used method is the third method, where we use penalty methods and add the PD residual to the loss function as a soft constraint. This is what most of the state-of-the-art methods apply nowadays, and we'll look into this in greater detail. The reasons to use this method is that it is very easy to implement and works with automatic differentiation on any neural network architecture. It does not require a mesh or a numerical solver for the PD, and in theory, it can approximate high dimensional problems and complex PDEs. For example, PDEs containing integral operators which are difficult to solve with finite difference methods can also be solved using this. Here we see a popular example of the Burger's equation. The Burger's equation is a partial differential equation where the differential of u with respect to t plus u into differential of u with respect to x minus 0.01 by pi times double differential of u with respect to x equals to 0. The support for x is -1 to 1 and the support for t is 0 to 1. The initial condition u of 0 comma x is minus sine of pi of x, and the boundary conditions are u at any time at x equals to -1 and 1 is 0. We can see that using pins with the penalty method and adding PD residual to the loss term as a soft constraint, the neural network perfectly predicts the output, and the exact analytical solution and the prediction overlaps completely as shown in the plots. Now we look into some other famous examples in more detail. Pins to solve a simple differential equation, A double differential of y with respect to x plus b dy by dx plus cy equals to 0. Here y hat is the full functional form of the solution of the differential equation. Now we look into the loss function development. So we first have a simple neural network architecture to predict y hat from the data, and we have a data fit loss Ly of theta, but to that we add the differential equation residual Lr of theta, the initial condition fit Ly naught of theta, and the boundary condition fit Lyb of theta. Three additional constraints that we have added in the loss function are minimizing the residual of the differential equation, which is this part, minimizing error in the boundary condition fit, which is this part, and minimizing error in the initial condition fit. But in this case, since there are no initial conditions, it simply equals to 0. But in more general cases, there will be a term for this as well. Now we look into the case for the pin to solve the Burger's equation in greater detail. This is the 1D form of the Burger's equation where u is a function of x and t. We can see that the neural network architecture is parameters over theta, position x, and time t, and u at t comma x is the full functional form of the solution. Through backprop, we get the gradients dou of dou t with respect to u, dou of dou x with respect to u, and double differential of with respect to x, and also the identity matrix. We already have the database loss term. Over that, we create the residual loss term of the differential equation, the boundary condition loss terms, and the initial condition loss terms, and we take summation of all those loss terms and then finally optimize using backpropagation and gradient descent. Now it is very easy to implement in any auto differentiation software, be it TensorFlow or PyTorch. We define the simple neural network. Then we define the pin where u is the solution function. We take u underscore t as the gradient of u with respect to t. Simply tf dot gradients ut 0. Similarly, gradients of u with respect to x, double gradients of u with respect to x, and finally the functional form f, which is the residual error loss. And we return f from the function. Now solving it using the above pin, we get the following solutions. We see that the initial at t is equal to 0 data points are the initial conditions. At x equals to 1 and x equals to minus 1, we get the boundary conditions. And finally, if we see the solutions at t is equal to 0.25, 0.5 and 0.75, we see that the blue exact match and the red predictions exactly overlap, and thus the solutions are very apt and appropriate. Now we look into the applications of pins as we discussed above in cases of Earth system sciences. I analyzed the paper Physics Guided Neural Networks, an application in lake temperature modeling by Kapatny et al. They present two of the following approaches. Using physics theory, they calculate additional features or simply feature engineering to feed into the neural network model along with measurements, and they also add a physical inconsistent term to the loss function in order to punish physically inconsistent predictions. In the paper, lake temperature modeling is taken as an example to demonstrate the effectiveness of PIN. Water temperature controls the growth, survival, reproduction of biological species living in the lake. Therefore, accurate observations and predictions of temperature are crucial for understanding the changes occurring in the community. The task is to develop a model that predicts the water temperature as a function of depth and time for a given lake. Now let's see how they applied first the feature engineering and second the loss function modification for this problem. For feature engineering, they use a physics-based model called the general lake model, which is open source and available easily on the internet, to generate new features to feed into the neural network system. It is a physics-based model that captures the processes governing the physics of temperatures in a lake and solves some simple differential equations to get those solutions. Heating due to sun, evaporation, etc. Let's now see how they define this physical consistency term. This is known that it is well known that denser water sinks. The relationship between water temperature and its density is thus known. Hence, correct predictions should follow the fact that deeper the point, the higher the predicted density. If for a pair of points, the model predicts higher density for a point closer to the water surface, that is physically inconsistent and should be highly penalized. Here, we take two points at depths A and B, A being closer to the surface, B being at greater depth. Now, predicted temperature at A and predicted density at A is rho A. Predicted temperature B and the corresponding predicted density at B is rho B. Now, it will be physically inconsistent if rho of A is greater than rho of B. In that case, a penalty has to be applied. Now, it is very easily possible to incorporate this idea into the loss function. We like to punish if rho A is greater than rho B and do nothing otherwise. Moreover, for a large inconsistency, punishment should be higher. This can be done easily by adding the value of the function max of rho A minus rho B, 0 to the loss function. If rho A is greater than rho B, the rho A minus rho B term will be positive and greater than 0, and thus max of rho A minus rho B, 0 will return that difference. And we'll add that to the loss function, thus increasing the loss function, which we need to minimize. Otherwise, it will give 0, leaving the loss function unchanged. At this point, two modifications are necessary to the function in order to use it properly. What is important is that we want the average inconsistency over all pairs of points, not a single pair of points. Thus, it is possible to take the sum of the max of rho A minus rho B, 0 for all sets of points, divide by the total number of pairs of points. Also, it is critical to control the relative importance of minimizing the physical inconsistency compared to the data loss. This can be done by simply multiplying average of the physical inconsistency with a hyperparameter. This works as a regularizing parameter. And the authors have tested 4 models: a general physics-based model, which they call PHY. It is a general lake model. A simple neural network-based model that acts only on data available and doesn't use any physics-based constraints. Pin 0, a neural network with feature engineering, results of the GLM are fed into the neural network as additional features, and a pin, which is a neural network with feature engineering and the modified loss function. Now, if you see the results, they have measured the results in terms of RMSE and the physical inconsistency, the fraction of time steps where the model made physically inconsistent predictions. They have shown the results for two lakes, that is Lake Mildax and Lake Mendota. If you see clearly, we see that comparing a neural network with the physics models, we can conclude that neural network gives more accurate predictions at the expense of physically inconsistent results. And comparing pin 0 with pin, we see that the physical inconsistency is eliminated mostly thanks to the modified loss function. Improved accuracy is mostly due to feature engineering with some contributions from the loss function as well. Now, to conclude things, we see that pins give very impressive results that are accurate and also physically consistent. Moreover, incorporating our knowledge of the world into the loss function, even as a simple regularizing term, as we saw in the lake modeling example, or as complex differential equation-based constraints, as we saw in Berger's equation previously, provides an elegant way to improve the generalization performance of machine learning models. This seemingly simple idea has the potential to fundamentally improve the way we conduct machine learning and specifically scientific research. Pins use knowledge of physical systems and the laws of physics as priors and invariants in training neural networks. Pins have enormous applications in scientific computing and helps mitigate some of the fundamental problems of deep learning systems like poor generalization in low data regime, helps create data efficient systems and make deep learning systems more robust to epistemic uncertainty, which is very important in scientific disciplines. Huge corporations like NVIDIA, Unity Technologies, and ANSYS are using pins extensively to create realistic simulations in game engines and in modeling and simulation based softwares. Similarly, scientific organizations like CERN are also using pins to analyze experimental physics results. Though pins are a very exciting field of research with lots of potential applications, there are still many open problems. Like current pin architectures and methods fail to learn many simple differential equation based problems such as advection, reaction, and or reaction diffusion problems with non-trivial coefficients. Analyzing the problem shows that while the neural network has enough capacity to learn the solution, the optimization problem with pin as a soft regulation often becomes difficult to solve. These are open areas of research with lots of scope for improvement. If you would like to explore the things in greater detail, you can look into the references. Firstly, the deep learning book from Ian Goodfellow, Yosha Benjo, and Aaron Conwell, and the wonderful physics-based deep learning book, which is openly available online from Neil Theory's group at Technical University of Munich. The two seminal papers, Physics in for Neural Networks, a deep learning framework for solving forward and inverse problems involving nonlinear partial differential equations, that was presented in Journal of Computational Physics in 2019 from Rice and co-authors. This is a group from Brown University, and the 1998 paper from Lagardis and co-authors. And for the specific case of applications of pins in system sciences, the Physics Guide in Neural Networks, and application in lake temperature modeling paper from Kabatne and authors are also a wonderful place to start exploring the field. Thank you. With that, I would like to end the presentation. Thanks for your attention.